properly sized bonding conductor connected to a conduit and the utility neutral at the utility pole does indeed provide an effective ground fault current return path and will trip the primary cutout if the conduit becomes energized. To understand why, let's delve into the fundamentals of grounding and bonding in electrical systems. Grounding refers to connecting a conductive object to the earth, typically through a grounding electrode system. Bonding, on the other hand, involves connecting conductive parts together to create an electrically conductive path that ensures electrical continuity and the capacity to safely conduct any fault current likely to be imposed. The purpose of grounding and bonding is to provide a low impedance path for fault current to return to the source, which is typically the utility transformer. This low impedance path facilitates the rapid operation of overcurrent protective devices, such as circuit breakers or fuses, to quickly de-energize the faulted circuit. Now, let's consider the scenario of a conduit becoming energized. This could occur due to a breakdown in insulation, a direct contact between a live conductor and the conduit, or some other type of fault. If the conduit is not properly bonded, it will become energized and pose a significant electrical shock hazard. Furthermore, without the proper return path for the fault current, the overcurrent protective devices may not operate quickly enough, or at all, to clear the fault. However, when the conduit is properly bonded to the utility neutral at the utility pole with a properly sized bonding conductor, several things happen. Firstly, the bonding conductor creates a low impedance path for the fault current to flow back to the source. This path is parallel to any other ground return paths that may exist, such as the earth itself. Secondly, the low impedance path allows a large fault current to flow. This large fault current is necessary to quickly trip the primary cutout or other overcurrent protective devices at the utility transformer. The primary cutout is designed to protect the utilities equipment and the distribution system from faults. When a large fault current flows through the primary cutout, it will rapidly interrupt the circuit, energizing the faulted section of the system. Thirdly, the connection to the utility neutral provides a direct electrical connection back to the source of the power. This connection ensures that the fault current has a clear and reliable path to return to the transformer. Without this connection, the fault current may have to find its way back through less reliable paths, such as the earth, which can have a much higher impedance. The size of the bonding conductor is critical. It must be large enough to safely carry the maximum fault current that could be imposed on it. The National Electrical Code, or NEC, provides specific requirements for the size of bonding conductors based on the size of the circuit conductors. For example, NEC Table 250.102 CON provides guidance on sizing equipment grounding conductors for grounding electrode conductors. The size of the bonding conductor must be adequate to handle the available fault current. The available fault current is the maximum amount of current that could flow in a fault condition. This is determined by the impedance of the source, which is typically the utility transformer, and the impedance of the circuit. If the bonding conductor is too small, it may overheat and potentially melt or vaporize under a fault condition. This could interrupt the ground fault current path and prevent the overcurrent protective devices from operating properly. In addition to the size of the bonding conductor, the quality of the connections is also important. The connections must be made properly to ensure a lower impedance path for the fault current. Loose or corroded connections can significantly increase the impedance of the ground fault current path, reducing the effectiveness of the grounding and bonding system. The NEC specifies requirements for the types of connectors that must be used for grounding and bonding applications. These connectors must be listed and labeled for the intended purpose. The connections must be made in accordance with the manufacturer's instructions. Now let's discuss some common misconceptions about grounding and bonding. Firstly, it is a common misconception that the earth provides a sufficiently low impedance path for fault current to return to the source. While the earth can provide a path for fault current, it is typically not a very good path due to its relatively high impedance. Relying solely on the earth for fault current return can result in slow operation of overcurrent protective devices and increased shock hazards. Secondly, it is a common misconception that grounding and bonding are only necessary for safety. While safety is a primary concern, grounding and bonding also play an important role in the proper operation of electrical equipment. Proper grounding and bonding can help to reduce electrical noise and interference, which can improve the performance of sensitive electronic equipment. Thirdly, it is a common misconception that grounding and bonding are only necessary for new construction. Grounding and bonding are important for all electrical systems, regardless of age. Existing electrical systems should be inspected and upgraded as necessary to ensure that they meet current code requirements. Now let's delve into some specific requirements of the NEC related to grounding and bonding. Section 250.4 of the NEC covers the effective ground fault current path. This section requires that the ground fault current path be permanent and electrically continuous, and have the capacity to conduct safely any fault current likely to be imposed on it. Section 250.92 of the NEC covers bonding of equipment containing service conductors. This section requires that all metal enclosures containing service conductors be bonded together. This includes service entrance conduits, meter enclosures, and service disconnect enclosures. Section 250.102 of the NEC covers sizing grounding electrode conductors and bonding jumpers. This section provides specific requirements for the size of grounding electrode conductors and bonding jumpers based on the size of the circuit conductors. Section 250.130 of the NEC covers equipment grounding and equipment bonding jumpers. This section requires that all non-current carrying metal parts of electrical equipment be grounded. This includes motor frames, appliance housings, and metal enclosures. Section 250.166 of the NEC covers grounding requirements for separately derived systems. This section requires that separately derived systems, such as generators and transformers, be grounded in accordance with specific requirements. Let's consider an example scenario. Suppose a 480-volt motor is installed in a factory. The motor is supplied by a three-phase circuit with three number 6 American wire gauge conductors and a number 10 American wire gauge equipment grounding conductor. The motor frame is connected to the equipment grounding conductor. If a fault occurs inside the motor, causing the motor winding to come into contact with the motor frame, a fault current will flow through the equipment grounding conductor back to the source. The size of the equipment grounding conductor must be adequate to handle the available fault current. If the equipment grounding conductor is too small, it may overheat and potentially melt or vaporize under a fault condition. This could interrupt the ground fault current path and prevent the overcurrent protective devices from operating properly. In this scenario, the equipment grounding conductor will provide a low impedance path for the fault current to return to the source. This will cause the circuit breaker to trip, de-energizing the motor and preventing a potentially dangerous electrical shock hazard. In summary, a properly sized bonding conductor connected to a conduit and the utility neutral at the utility pole will provide an effective ground fault current return path and will trip the primary cutout if the conduit becomes energized. This is because the bonding conductor creates a low impedance path for the fault current to flow back to the source, allowing a large fault current to flow, and provides a direct electrical connection back to the source of the power. It is important to ensure that the bonding conductor is properly sized and that the connections are made properly to ensure a low impedance path for the fault current. It is also important to understand the requirements of the NEC related to grounding and bonding. By following these guidelines, you can help to ensure the safety and proper operation of electrical systems. Remember that electrical work can be dangerous. Always consult with a qualified electrician before performing any electrical work. They can help you to ensure that the work is done safely and in accordance with all applicable codes and regulations. By understanding the principles of grounding and bonding, you can help to create a safer electrical environment. This knowledge is essential for electricians, engineers, and anyone else who works with electrical systems. The NEC is a complex document, but it is important to understand the requirements related to grounding and bonding. By following these requirements, you can help to ensure the safety and proper operation of electrical systems. If you have any questions about grounding and bonding, consult with a qualified electrician or electrical engineer. They can help you to understand the requirements and to ensure that your electrical system is properly grounded and bonded.